1.1.1. This is about as stock standard as they come. So that's just going to be x plus 1, x plus 1 in its factorized form. That's all equal to 0. As standard form demands, thusly x is equal to negative 1 or x is equal to negative 1 is a gigantic formula that you can use as well. Now, let's have a look at 1.1.2, which states that we have x multiplied by 5x minus 3, and that's all equal to 1. So let's distribute the x into those brackets over there, which gives us 5x squared minus 3x if we do that correctly. Now, we'll just subtract 1 from both sides because we want this is equal to 0 present. Standard form. And then, of course, that zeroes out on the other side. And, yeah, about that formula. X is equal to, well, minus 3, because that is our B value. Our A value, of course, is over there. And that is C, if we do it correctly. Well, back to this structuring of the big fraction. Plus minus the square root of b squared, that's minus 3, all squared, minus 4, value of a, of course, as previously stated, is 5, and minus 1 for the value of c, all divided by 2, well, multiplied by, in this case, 5, and that is equal to, after some beautiful editing, minus 0, 24, or 0,84. Yeah, 2 decimal places. 1.1.3 gives us a quadratic inequality. So let's deal with that. So we'll have 2x plus 3 being greater than x squared. Everything to the left for standard form will give us negative x squared, because that is what we subtracted from both sides to get a 0 on that side. Plus 2x plus 3, that's all greater than 0. Of course, we want our leading coefficient, this number in front, to be positive, so we'll do that by multiplying or dividing by negative 1 right through. That'll give us x squared minus 2x minus 3. We'll still have a 0 on this side, but because it was a negative that we were dealing with, the inequality sign flips, giving us this, and now we can factorize. We'll get x minus 3, x plus 1, or less than 0, of course. Again, there's a formula over there. So our critical values will equal 3 or negative 1. Because we now have this positive leading coefficient, we are dealing with a smiley face parabola in our little sketch, giving us negative 1 on the left and 3 on the right. Now do we read this? Well, everything above this little axis is positive, everything beneath it is negative, and we want the stuff underneath, which means we are dealing with that continuous area between negative 1 and 3 as our boundary values. And of course, that is the final solution. Let's clean up the board and get back some space. Ooh, almost. Okay. So, over here we have a principal root equation, which states that the square root of 7x minus 12 minus x is all equal to 0. Thusly, well, 7x minus 12, the square root thereof, is equal to x, because we added x to both sides. Now we can square both sides. Why? Because we have made sure that we have our principal root isolated, meaning it's alone, it's the only thing on the left hand side, which gives this mechanism the opportunity to work as intended. So we square that side and we square that side, giving us 7x minus 12 all equal to x squared. Of course, we'll move everything or transpose everything from the left to the right. Let's do that in a different color. So we'll subtract 7x on both sides and just add 12 on both sides as well, giving us 0 all equal to x squared minus 7x, because what we do on the left we do to the right, and then plus 12, again following the same logic. What we do to the left we do to the right, which now gives us as factors 0 is equal to x minus 3, x minus 4. Well, there's still a formula-sized formula on the information sheet, but in this case we have thusly x is equal to 3 or x is equal to 4. And because this is a principal root equation, we need some verification to make sure everything works or otherwise. So let's see, if we use 3 in this step, let's clean this up quickly. No. Undo that. Let's use this step over here. Let's use this step over here. This one over here. So, using 3, we'll have 7 times 3 is 21, minus 12 is just 9, and the square root of 9 is 3. If we sub in the 3 over there to that x, that's just 3, so everything works out. So that checks out. How about 4? Well, 7 times 4 is 28, minus 12. 28 minus 12 gives us 16, and the square root of that is 4. And then 4 is just 4. Remember, I didn't square when I was verifying. I ignored that. I just wanted to make sure that these values come out the same on both sides, and they do. And that's the last mark allocated for a problem like that. Next, we have something of an exponential quantity. Let's see how that goes. Well, a quick check will see that 216 is equal to 6 to the power 3. I'm partial to colors. So now knowing that, that means we don't need to do anything with this 1 over 6 value over there, other than applying the definition that we learn in exponent laws, which states that 1 over a can be rewritten as a to the power minus 1. So we'll see that over there in play. And we'll have 3x plus 2 as the exponent. We didn't change any values. 216 then becomes 6 to the power 3 as discovered over there, and that's just 3x. Now, if we combine this logic, well, that's 6 to the power 3, but because it's in the denominator, we'll change it to 6 to the power negative 3. Let's just use an eraser quickly. Little box is in the way. Yeah. Okay. That's a negative 3. Let's see where all this takes us. That'll be 6. Well, minus 3x minus 2. That is 9x. So we'll add that. And that's all equal to 6 to the power negative 3. Which means we can now compare our exponents, which gives us, well, 9 minus 3 gives us 6x. So 6x minus 2 is equal to minus 3. Let's just add 2 to both sides. So 6x is equal to, oh, that's just going to be minus 1. Which means x is equal to minus 1 over 6 after we've divided both sides by 6, of course. That's a really ugly 6. Yeah. No question 1 would be complete without a simultaneous set of simultaneous equations or a system of equations. So let's label these. That's our first port of call. 1 and 2. And then from equation 1, of course, we'll have that. Let's see, I'm going to do x, and that's going to equal 3 minus y. That's the third equation we create. Okay, so we'll box this. Nice, package friendly. Therefore, we can now sub 3 into, well, what equation haven't we used yet? Of course, number 2. Flip colors again, and that'll mean we'll have, well, something squared because it's ready for the box, for the package to be delivered, and that's plus 2 times y squared. That's all equal to 18. What is the something we want to square? Well, 3 minus y, of course. So let's deal with this. This expansion that we have from the square, binomial squared. That's going to be 9 minus, well, 3 times minus y is minus 3y, and then multiplying that by 2 means we get minus 6y, and then of course plus y squared. Again, first term squared for the second term, front times back times 2, and then for the back we have, well, the back part squared, and that's all plus 2y squared. Then we can of course subtract 18 from both sides to transpose that 18. We'll have everything equal to 0. So, like term collection time, that's going to be 3y squared. Then we'll have minus 6y. And of course 9 minus 18 is minus 9. That's all equal to 0. Dividing everything by 3. Let's see if we can do something over here. So we'll have y squared minus 3. That would have been a costly mistake. Minus 2y, of course, minus 3, and that's all equal to 0, giving us as factors y minus 3, y plus 1, that's all equal to 0. That means we have that y is equal to 3, y is equal to negative 1. Those are 2 options. And then for the x values that need to accompany these, of course we'll use equation 3. We'll have x, well, 3 minus 3 gives us a 0, and 3 minus minus 1 minus minus 1 gives us a, gives us that x is equal to 4. Given the square root of 5 all to the power x minus the cube root of 2 all to the power y being equal to 17, where x and y are members of the natural number set, determine a value for p that is defined by x multiplied by y. So that is a mouthful. We have 17, so we'll have 5 to the power, I'm going to use a, minus 2 to the power, well, some b value. Now, is there a power of 5, and then we subtract a power of 2, which are both small enough such that we get a difference of 17. Now, either you see it or you don't, but 25 minus 8 is equal to 17. Now that gives us a starting point to work with, because we can restate this as 5 to the power 2 minus 2 to the power 3. That's going to equal 17 still. Now, why does that help us? Well, if we can rework this, we'll get some expression that'll turn into an equation. The same is true for that term right over there. So let's get to working. Well, the square root of 5 to the power x can be rewritten as 5 to the power 1 over 2 all to the power x, which is equal to 5 to the power x over 2 in its final form. That means x over 2 being equal to 2 under this presumption, not assumption, we'll have that x is equal to 4. Then we'll do the exact same thing mechanically for the other term, we will have, well, the cube root of 2 all to the power y can be rewritten as 2 to the power 1 over 3 all to the power y, which is equal to 2 to the power y over 3. And then I'll take that, y over 3, and equate it with 3, of course. Again, we go back to our initial presumption. Therefore, y is equal to 9. So they asked us to determine a value for p. That would mean p being equal to x times y. So that's a value for x we now have, and a value for y. That is going to equal, well, 4 times 9. And that's all equal to 36. 36. Now this is an interesting problem right off the bat. It says the following geometric sequence represents the areas of the squares in centimeters squared as drawn below. So let's just remind ourselves how a square works, in case it's relevant. Well, a square is just a quadrilateral where all four sides are equal. And then to make the area calculation easy, the internal angles, the 4 internal angles, are all equal to 90 degrees, which means we have for the perimeter 4 times whatever the side value is. And then for the area, so that's perimeter, for the area we have side squared. So that's all important information. So these are the areas, which means that is 6 squared, that's been divided by 2, that's been divided by 2, and of course that's been divided by 2. We can see that r is equal to a half over there, but maybe I'm getting ahead of myself. Let's move. Does the series converge? Justify thy answer. And I know what I said. I'm aware of it. I stand by it. Well, we had 36 plus 18 plus 9. So r is equal to t2 over t1, which is equal to t3 over t2. And in this case, that'll give us 18 over 36, which is equal to, this is just me being unnecessary with the 9 over 18. But those are all equal to half. I just want to fully impress the point upon everybody that r, the ratio, which is constant by definition, is equal to 1 over 2, and that is greater than negative 1 and less than 1. Thusly, series converges. That is straight from our formula sheet as well. Let's clean this up. Come now, let's clean this up. It's clean. And bring back whatever information is pertinent. In this case, that r is equal to 1 over 2. Calculate the sum to infinity. Well, the sum to infinity, according to the formula, looks like this. That's the first term. And then as the denominator, we have 1 minus r. So that'll be 36 divided by 1 minus 1 over 2. Yeah, and based on prepped information, we have 272 centimeters squared. 72 centimeters squared. Again, cleanup trick. Which square will have a side length of 3 over 8 centimeters? Well, for that, the side series, which square will have a side length of 3 over 8 centimeters? Well, let's just do our general term first, which is 36, because we have to conform to a times r to the power n minus 1. Our ratio, of course, is 1 over 2 and then n minus 1. So we're going to take this and make it equal to 3 over 8 all squared, because this tracks the area. The area. That's what our series tracks. Now, from all that, we'll have 1 over 2 power n minus 1, and that's all equal to 3 over 8 all squared times 1 over 36, because we divided both sides by 36 to get here. From that, of course, using our calculator, we'll find that we should have 1 over 256, which is of course 1 over 2 all to the power 9. That logic is easy to track using a little bit of calculator trickery. What do I mean by that? Well, let's bring in a trusty calculator. Well, that 256, we'll just take that, do that, and then shift and fact. So if you happen to have a calculator that does that, you'll see that I made a slight calculation error for trying to work from memory. So let's come and fix my nonsense. And of course we'll have that needs to be an 8, of course. Therefore we have the same basis, so n minus 1 is equal to 8 now. Therefore n is equal to the 9th square. So over here what we'll have is n is equal to the 9th square. So let's clean up once more so we can have our space back. And that's efficient. Calculate the sum of the diagonals of the first 10 squares. So what we'll have is that the diagonal is going to depend on the side length, and then we'll use Pythagoras. So for that we'll have 6 squared plus 6 squared, that's equal to what? 72. That is just from Pythagoras. So again, we're talking about the diagonal over here. Now, that diagonal is obviously going to equal the square root of 72. And if we take that into its third form, that will be 6 multiplied the square root of 2. So let's just do a second one over here for the second square, which has an area of 18 square centimeters. Of course, the side length over there is going to be the square root of 18. Now, to get its diagonal, what we'll do is we'll take the square root of 18 all squared plus the square root of 18 all squared, and that's going to equal, well, look at that, 36, which means therefore diagonal 2. So that's diagonal 1, diagonal 2 is going to be the square root of this, square root of 36, which is equal to 6. So over here we have 6 times the square root of 2, and we have 6. And if we take that and continue the pattern that is obvious over there, what we'll find is the following. We have 6 square root 2 plus 6 plus 3 square root 2, and so on and so on and so on, which means our ratio is going to equal 1 over the square root of 2, because that's what we're dividing every term by to get the next diagonal's length. Okay, I encourage you to stop the video and double check that my term 3 is not some thumb-sucked value. There is nothing wrong with double checking your facilitator, your tutor, or your teacher, but once you have that sorted, then you will have verified the logic that you are being shown and or taught. Now, they want the sum of the diagonals of the first 10 squares. So, given that we have r, we have an a value which is equal to 6 times the square root of 2. I think we are ready because we have an n value that's equal to 10, of course. So let's do that in a different color. Orange is good, I think. So we'll have the sum to n terms is of course equal to a, that's r to the power n minus 1 all divided by r minus 1. Substitute those values. A is going to be 6 times the square root of 2, 1 over square root 2 to the power 10, of course, minus 1, and that's all divided by 1 over the square root of 2 minus 1, which gives us 28,07 and some other digits. That's not important. What's important is they wanted the sum of the diagonals, plural. Well, the one thing we've been avoiding, not we, me, because I'm doing this here through the magic of virtuality, is that, well, every square happens to have two diagonals, ones that I'm really badly drawing now, which means all we need to do is take this, which is the sum to 10 terms of one diagonal, and then just double it. So multiplied by 2, okay, each square has 2 diags, and then we'll have 56,14 cubic centimeters, and that's of course not cubic centimeters, square centimeters. That is of course rounded to 2 decimal places as per the requirements under caps. What's next? The 7th term of an arithmetic sequence is 4, and the 12th term is equal to 14. So let's state that using algebra. So the 7th term is 4. So that is what? Well, that's the first term plus 6 common differences. That's equal to 4. This is very important theory that we sometimes ignore. And then for the 12th term, we've been told it's the first term plus 11 common differences, and that's of course equal to 14. So that's just the bit of theory that says it's, well, a plus the common difference plus the common difference plus the common difference, and that is how any arithmetic sequence adds up. So term 1, a of course, term 2, term 3, term 4, term 5. You can see where I'm going with that. But over here we have set up simultaneous equation, and we have the opportunity to do some Gaussian elimination. I mean by that, well, we're just going to take the first equation and subtract the second equation, term 12. Where does that lead us? Well, it leads us to the use of the green as a separate color, so that we can have a 0 over there, and then that's just going to be minus 5d, and then that's just going to be minus 10. Thusly, d is equal to 2, because we divided both sides by negative 5. Of course we did that. Then, from the first equation, I'm just going to take this, d, and punch it into that. So we'll have a plus 6 times 2, all equal to 4. And that means a is equal to, well, that's minus 12 to 0 this out, and minus 12 over there. Because what we do to the left, we must do to the right, and that's minus 8. And that's, well, common difference, and that's the first term. So that's T1, and that's our common difference. I think that's cool. So let's just transfer that information over here. So D is equal to 2, and A is equal to negative 8, which gives us the opportunity now that we have a clean board, which term of the sequence will be the additive inverse of the first term? So first things first, A is equal to the first term, which is equal to negative 8. Now let's deal with this concept of an additive inverse. Well, that's just asking, if I have some number A, well, what number must I add to A to make sure that I get a 0? So you could have instinctively reached for some negative A value, which means therefore the additive inverse, so minus a is equal to minus 8 is what we need. But that's not what they want. They want to know, not minus 8, plus 8, sorry. I'm going to stick to this sequence, this explanation. So the term we're looking for needs to equal positive 8. So first things first, let's just construct our general term firstly. So using our formula sheet, we have a plus n minus 1 times d. Or we can just realize that we're dealing with something that's like 2n. What's our first term? Minus 8, and we have to subtract 10 to get over there. Therefore, 2n minus 10 is to equal what value? 8. So 2n must equal, let's add 10 to both sides. Because what we do to the left, we do to the right, and we have 18. Now, if we divide both sides by 2, n must equal 9. So therefore, term 9 is the culprit we are looking for. Let's just do that. That's not really a 9, ugly as it is. Well, given some sigma notation being equal to 19,995, determine the value of k. Well, what does the sigma notation read? Well, it wants the summation of the general term 4p minus 1 from where we have the kth term to the 100th term for this specific series. So first things first, let's just flesh this out. Our first term is going to equal, well, four times 1 minus 1 is equal to 3. Our second term for this is going to equal 4 times 2 minus 1, which is equal to 7. Making our common difference, well, d is just going to equal d2 minus d1, which is equal to 4. So I can do this, just general for this. If we're taking from term 1, whatever, we don't know what the value of k is. That is understandable. We are here to find out the value of k, but we can get the 100th term as well. So t 100 is just going to equal 4 times 100 minus 1, which is equal to 399. From that, of course, we can now attack this summary as is, and that summary, of course, points to a summation as described, which means we're going to use our summation formula. But we're going to use this version, which says is subscript n is equal to n over 2 multiplied by the first term plus the last term. So what does that mean? Well, let's see what we have. We have the sum to n terms, that is 19,995, and that's obviously equal to, well, how many terms do we have? Well, to determine this, we're going to use our normal logic. If we want to know how many terms is in the sigma notation, it's top 100 minus bottom, which is k, and then plus 1. So that's the specific case. But in general, it's top minus bottom plus 1. That'll give you the number of terms over there. Now, that means 100 plus 1 is 101 minus k. So that's the value of n for this calculation. So let's plug it in. So that will give us 101 minus k over 2. What's our first term? Again, because we're doing the generalized version over here and we want the value of k, we are going to have 4k minus 1 plus what's our final term? 399. That's the value of L over here, which we did calculate. Right there. Keep changing colors just to make sure that we don't get confused. So we're going to multiply everything in this equation by 2, giving us 39,990 on the left And then on the right we'll have, well, 101 minus k. That's multiplied by, well, if we do that addition we get 398. So we'll have 4k plus 398. This up, this is what we're left with, because that's 404 minus 398 gives us that, and 39,990, and subtracting of course 40,198 gives us minus 208. Well, if we take the quadratic formula to this, because there is no way I'm going to try and factorize it, we get that k is equal to 8, or k is equal to negative 13 over 2. This is obviously invalid, because the iteration counter that we have over here, that's what I call it, that iterates from the bottom number to the top has to work in natural numbers. That's positive integers. Therefore, k is equal to 8 is our logical answer to this problem. That's going to be an editing headache. Consider the quadratic number pattern 3, 12, 33, and 66, and so on and so on and so on. Write down the value of the next term of the quadratic number pattern. So we have 3, 12, 33, 66. That's 9, 21, 33. Get from there to there. 12, 12. There we go. So yeah, now that we've fast forwarded through everything over here, that's just throwing up the pattern and getting to that. So if the general term of the quadratic pattern is that, okay, so just accept that, determine the value of the 9th term minus the 5th term. So d9 minus d5. So the question is, do you know how to do substitution? Well, we have the 5th term right over there. So d9 is just going to equal 6 times 9 squared minus 9 times 9 plus 6, which is equal to 411. Therefore, d9 minus d5 is equal to 411 minus 111, and that's just equal to 300. Let's move. The following information of a quadratic pattern is given. The general term has the form an squared plus bn plus 1. The 4th term is equal to 27. And then the 3rd term minus the 2nd term is equal to 8. So what are we going to do with this information? We are going to use it to determine the values of A and B. How does this work? Well, let's work from the bottom. Term 3 is just going to be, well, A times 3 all squared plus B times 3 plus 1, because we did a thing. So that's just going to equal 9A plus 3B plus 1. And then of course we know that if we subtract the 2nd term, we get 4A plus 2B plus 1. That's going to give us the exact same thing. And that means we now know that 5A plus B is equal to 8. So let's just stop there. Okay. So remember, I took I took the value 3 and subbed it in here. That gave us this. Now if I want to do the same thing with the 2, I'm going to get that. Why? Because they say t3 minus t2 is equal to that. So there we have that. 9 minus 4 gives us 5. And then 3 minus 2 gives us 1. And 1 minus 1 gives us 0. And they tell us that it's equal to 8. So there, I got one equation. So first things first, a little bit of cleanup over here. Because I managed to ignore the limited space I'm working with. Also, now term 4 is equal to, well, a times 4 all squared plus b times 4 plus 1, and that's equal to, well, 27. So let's have a look at that. That tells us that 16b plus 4 so that tells us that 16a plus 4b is equal to, subtract 1 from both sides, 26, and that gives us equation 2. So why is that important? Well, we can now do a bit of Gaussian elimination over here. How does that work? Well, we're going to take this b, we're going to take equation 1 and multiply it by 4. Because we realize that in the second one, we're going to take this b and compare it to the second b. We know that equation 1 times 4 now gives us, well, 20a plus 20a plus 4b, and that's equal to 32. And then equation 2 we can leave as is. That's just going to be 16a plus 4b, that's equal to 26. And then we'll just say that this is equation 3, and then we'll have 3 minus 2 all equal to, well, 20 minus 16 gives us 4 for what? 4a. Well, the point was to eliminate the b's. And then we'll have, of course, over here 32 minus 6 being equal to 6. And then from there, we can save this over here and say that a is equal to 3 over 2. Well, we can divide both sides by 4. And that gives us 3 over 2 in its simplified form. How are we going to get the value of b? Well, first things, let's just get a bit of space. Yeah, that's going to be enough. We will say, using 1, 5 times 3 over 2 plus b is equal to 8, and then b will equal 8. 8 minus, well, what is that? 15 over 2. Therefore, b is just equal to 1 over 2. Check that with a calculator. That was messy but good. Where are we? Given the function z of x is equal to x squared minus 2x minus 3, and g of x is equal to x minus 3, where x is a member of the reals, sketch the graphs of the two functions f of x and g of x. So let's start with making sure we have enough. Let's start with making sure that we have enough data for all of this. So we need x-intercepts, and then we need the y-intercept as well, and the turning point. Just one. So let's start with the x-intercepts, because we know that all y values on the x-axis are equal to 0. We're going to take this and make it equal to 0. So that's just going to be x squared minus 2x minus 3 is equal to 0. So you could use the formula, or you can just Factorize. Therefore, x is equal to 3 and x is equal to negative 1. For the y-intercept, well, this is standard form, so we can just read that c value, and we'll say that that is equal to negative 3. Then, of course, the turning point, we'll have that p is equal to minus b over 2a. And that is going to equal 1. If we follow this, remember, ax squared plus bx plus c. So that is that. And then if we punch that into our function, then we'll find that f of 1 is equal to, well, let's see, 1 squared minus 2 times 1 minus 3. Use a calculator and you'll find that is equal to negative 4. So let's just find a place for all this data. I think called x ints. Then we have 3 and negative 1. So this is not formalized, this is just for us. Our y int, of course, that c value is negative 3. And then our turning point, that is going to be 1 and minus 4, of course. So let's clear the board. There we go. Well, for g of x, which happens to be a straight line, y is equal to mx plus c. The y-intercept also equal to negative 3. Just from the c value once more. And then our x-intercept, just going to make that equal to 0. So x minus 3 all equal to 0. Thusly, x is equal to 3. So there we have a framework for, well, drawing sketch. So what you'll find now is a little bit of editing. Well, okay, that does that. So we have our turning point over here. We have our y-intercept clearly marked for both f of x and g of x. We've got x-intercepts over there. Well, if somebody wants to get pedantic, we can do that in coordinate form as well. And 0, here we have that. And then, of course, this is 0 and negative 3. So, check with your teacher in terms of what they prefer. Again, like I said in previous videos, take me to task if I don't at least label my axes as is required. Big fat 0 at the origin. So, determine the values of x. Okay, so the answer has to be x is equal to something, x is greater than something, x is less than something. 4.1.2. For which, of course, f of x is greater than g of x. So what do they actually want over there? Tell us where f, which is the parabola, is greater than g. So that's still in math terms. What it actually means is we want to know where f is above g. So it's over there and it's over there. So we can see what's happening. This is where f is above g, as this requirement states. Now all we need is to track, okay, what are the x values for which that is true? We can see over there. Well, it happens to happen here at 0 and there at 3. So therefore we can see any value less than 0 is where this happens. So x is less than 0. And then, of course, also x can be greater than 3. That makes this statement true. Now, for the next part, we want to know, well, tell us where f of x times g of x. What is that? Okay, tell us where this y value multiplied by that y value gives us a negative product. Okay, so when we multiply stuff, the answer is a product, and saying anything is less than 0 is saying that it is a negative value as opposed to a positive value which needs it to be greater than 0. Okay, so now that we've got that sorted, so tell us where the y value from f times the y value from g gives us a negative answer, because that is what this means. So let's just have a look. Okay, so we need to know where the y values of f are positive and negative. So for f, let's have a look at the top. Over here, we're going to track those here. So we can see here at negative 1, everything is positive. Everything to the left of negative 1, of course. And then between 1 and 3, the y values for f become negative. And then after 3, the y values for f become positive once more. So, well, that tracks that, of course. And then, let's have a look over here. We can track g at the bottom. Well, there's only one point to track, and it's this one over here. Everything to the left of 3, the y values for g are negative, and to the right of that, the y values for g are positive. So it looks like we have 3 zones all in all to take a look at. Negative 1, and then from there to the value 3, and then obviously to the right of that. So let's just have a look at what happens. Well, to the left of negative 1, we have a positive y value times a negative y value. So everything is negative over there. So let's track that. To the left of this, everything is negative. And then between negative 1 and 3, what happens over here? Well, over there we have a negative y value for f and a negative y value for g. So everything is positive over here. And then, of course, to the right of 3, we have a positive y value for g and a positive y value, a positive y value for f and a positive y value for g, which means everything is positive over there as well. So the only place where everything is negative is where x is less than negative 1, or less than x is less than or equal to negative 1. So this is the answer for A, and this is the answer for B. So it's a rather messy explanation. Maybe rewinding it and taking it slow, or taking me to task if there's really a lack of clarity. Either is good. Now, finally, for this specific slide, we want to know the range of h if h of x is equal to negative f of x plus 4. Well, what does this do? So we are looking specifically at f's behavior. So the first thing they tell us is that, well, this entire thing turns around. So that's the negative part. All the y values get flipped. So that means we are looking at its reflection in the x-axis. Then what also needs to happen is, once we've taken care of that, is, well, there's a plus 4 thing that happens. So we can look at it like this physically, to see what that plus 4 entails, because the plus 4 is not going to take it up, it's going to take it down to there. But let's see if we can sort this out algebraically as well. So in order to do that, well, I think we deserve a bit of space. So I think this is going to be enough space over here. We'll tackle it in orange. So 4.1.3, of course. H of x is equal to negative, well, f of x plus 4. Now remember, just as we can substitute an x value, we can substitute a y value as well, and we do have the thing in turning point form is what will be preferred. So we're not going to substitute this, we're going to rewrite it in terms of turning point form, which means we'll have f of x is equal to, well, x minus 1 all squared. So we take the p value in there because we are using this this form of turning point form. Because we are using this version of turning point form, which is x minus p all squared plus q. So the a value over here is 1, because that is the a value in the standard form that we were given. So there's 1. P we get from our turning point, which is 1 over there. The negative or the minus sign belongs to the form. So we punched in the 1, and then of course our q value is minus 4. Whether we take it from the graph or not. Okay, so now we've successfully substituted f of x, and then it says plus 4. From that we can see we'll be left with, well, just x minus 1 in brackets all squared with those values equating to 0. So we've just reflected this thing correctly. So what we will be left with is x minus 1 all squared. There. So what is the range of this thing now? Well, we now have a frowny face parabola with a q value equal to 0. That means for 4.1.3, our range is that y is less than or equal to 0. So what we can see is, first interpretation would be physical one, flip it, and then instead of moving it up, realize that this negative means you are moving it down by 4 units. So your new parabola sits there. Or we can just do a substitution and finish the algebra, and from there we read the q value as 0, and then from that we just follow the way we normally do the range of any parabola. Between the shape and the y value of the turning point, we apply the correct logic. The following information of a parabola P, sketch below, is given. Ta-da! That's P. The coordinates of the turning point are 1 and 8. Nice. P prime of x is equal to negative x plus 1. So that is the gradient. Doesn't matter where you are or how the gradient changes, it is given by this little equation over there. The gradient of the tangent at point A, an x-intercept of P, is 4. So somewhere over here, the gradient of the tangent is 4. Also happens to be the x-intercept. Determine the equation of the parabola in the form y is equal to. So let's take this. We know that p prime of x is equal to 4 at A. That's what this piece of information says, but we have information about that gradient, which is p prime of x. The derivative is an actual gradient. So what we'll do is we'll substitute this with that. So we'll say minus x plus 1 is equal to 4. Remember where this happens? At point A. So minus x, I will subtract 1 from both sides, is equal to 3. If we follow this, remember this is an x-intercept. We want the value of x over there. So we just multiply everything by a negative right through. And we get that x is equal to negative 3. Which checks because it's to the left of that equation. So we have some information now to add to the diagram. That's minus 3 and 0, of course. Nice. Now we have the coordinates of the turning point being 1 and 8. So we are going to use turning point form and say that p of x is equal to a. We don't know the value of a. We'll have x minus 1 from this x value over there, all squared, plus 8. Now, the point of this entire calculation becomes clear over now. Becomes clear now because we can substitute that into this as well. So of course over there the y value is 0. That's what we get. And then we'll have a multiplied by, of course, minus 3. And then we still have minus 1. That's all squared plus 8. So what do we have? Well, that's negative 4. Negative 4 squared gets us 16. So that becomes 16a. And then subtract 8 from both sides, of course. That zeroes out. And what we do to the right, we do to the left. Thusly, a is equal to, well, we divide both sides by 16. You see, it ends up being minus 1 over 2. Can do better. A is equal to minus 1 over 2. Ugly but true. Now, what do they want? The equation of the parabola in the form y is equal to, well, ax squared plus bx plus c would be the form that they asked for on the question paper. So let's just complete that calculation. Space first, space. We always need space. Well, our turning point form says y is equal to 1 over 2, but negative, multiplied by x minus 1 all squared, and then our q value is 8. Apologies. Radio. So what we'll have is y is equal to negative 1 over 2 x squared minus 2x plus 1 plus 8. Multiplying all this in, we'll get minus 1 over 2x squared plus x minus 1 over 2 plus 8, of course. That gives us minus 1 over 2 x squared plus x, and then this will be plus 15 over 2, or if you so prefer 7,5. That's the decimal value, but I think for me p of x looks good enough in this form, that is standard form. Yeah, I cut off this question somewhere over there. Just became ugly for the slide. Okay. Here's another graph to analyze. In the diagram below, the graphs of f of x is equal to 2 divided by x plus b plus q, and g of x is equal to b to the power x plus 2. Those are given with the point A with coordinates 3 and 29 on G. Well, G is our exponential graph over here. So let's just see what all of this means. Yes, we'll see. Okay. They want us to write down the coordinates of B over here. Remember, they're telling us to write it down. Now, first things first, B is a point on both G and F, but we're going to take G. If you want to figure this out, we can see that 2 is the horizontal asymptote as displayed by the Q value on the graph, as well as the Q value within the defining equation for G, which means this is just going to be 1 unit up, and those coordinates are 0 and 3. It's a fairly complex explanation for a fairly simple concept. It's just going to be 1 unit higher, because whatever the base B is, the x value is 0. So anything to the power 0 is 2, and 2 plus 1. So just remember that it doesn't matter what B's value is, the x value is 0, and anything to the power 0 is just going to be 1, and 1 plus 2 gives us 3. Now, write down the range of g of x. Well, for the range we have y is greater than 2, because this is the asymptote, and we can see that g exists all over the show above that asymptote. This is mathematically the way we write it down. And remember, adding a classification for that range. What do I mean by classification? It's a real value system we're working with. All the values greater than 2 are still real values. Now, determine the value of b. Well, you weren't given this value of a, or the coordinates of a, 4, and j. Might as well use them. So, sub 3 and 29 into f, no, not into f, into g, and we shall have that 29 is equal to b to the power 3 plus 29. No, not plus 29. Plus 2. Well, subtracting 2 from both sides, we get 27, and we get 0 over there. So b cubed is equal to, well, 27 is nothing other than 3 cubed. And based on that, because the exponents are the same, we can say thusly b is equal to 3. So b is equal to 3. B is equal to 3. Board is equal to cleared. Determine the coordinates of C, the x-intercept of f, that little thing over there. So, first things first, we are working with f of x, and we'll change the color to say that it's equal to 2 over x plus b plus q, and then from our asymptotes, f of x now becomes, well, 2 over, well, this is minus 2, so that's going to be x plus 2, and then of course we have a plus 2 over there. Now, in order to calculate the x-intercept for any function whatsoever, for our x-intercept, y equal to 0, therefore we have 0 is equal to 2 over x plus 2 plus 2. Subtract 2 from both sides. Therefore we're going to have minus 2 is equal to 2 over x plus 2. We can cross multiply if we put the negative 2 over 1, and doing it in that form gives us, well, minus 2x minus 4 being equal to 2. Add 4 to both sides, and negative 2x becomes equal to 6. Therefore x is equal to negative 3. Minus 3 and 0 right over there. So let's see if we can just quickly re-enter every value we have. I think that value was important, and then over here we had 0 and 3. Those things were important, of course. Our value of b was equal to 3, so that's 3 to the power x plus 2 if we want a complete reinterpretation of g. Okay, 5.5. If h of x is equal to g of x minus 2, so let's write that down because I like doing that. That's 5.5. So g of x minus 2. Determine the equation of the inverse of h of x in the form y is equal to, well, some equation. So first things first, we'll take g of x and we'll sub it in over here. We can substitute y values. In the same vein, we can substitute x values because we won't be able to do the inverse of h if we don't know what it looks like. So without further ado, this becomes 3 to the power x plus 2. So there, we've substituted that. Maybe we can do that in a different color. Okay. I've just made sure that we substitute g of x. And then of course, we have to subtract 2. Well, 2 minus 2 is equal to 0. Therefore, h of x is equal to 3 to the power x. Now, for the inverse of h of x, what will we have? Well, first things first, we need to swap x and y values. We'll have that x is equal to 3 to the power y. And then from that, remember that the answer to a log is an exponent. So we want to say that y is equal to, because that is what they want, log base 3 with an argument of x. And that answers 5.5. So what are we going to say over there? Well, I think we can do that. Log base 3 x. Now, determine the equation of the axis of symmetry of f, which has a positive gradient. So remember, f is this hyperbola that we were dealing with, and its axis of symmetry run in a positive direction with a gradient of positive 1, and the other one runs with a negative gradient, but a specific negative gradient of negative 1. Now, y is equal to mx plus c, and we have a point. So the point of intersection for the asymptotes is also the point of intersection for these two axes of symmetry. So we will say that after subbing in, well, negative 2 from our vertical asymptote and 2 from our horizontal asymptote into, well, y is equal to x plus c. We will have, well, 2 is equal to minus 2 plus c. Therefore, c is equal to, well, add 2 to both sides. C is equal to 4. Therefore, y is equal to x plus 4. Okay, for which values of x is f of x times the derivative of g less than 0. So again, these are y. This is a y value we're tracking, f of x, and the derivative of a function is also a function, but we just have to be careful about it. So let's tackle that first. What is the derivative of g? Well, we don't need to know. What we can say then that is, well, this is an increasing function from left to right, which means it doesn't matter where I measure the gradient. Even though I don't know what it is, I know that it's always going to be positive. So g prime of x is greater than 0 for all r, for all real values. What about f of x? Well, we can have a look at f of x. F of x is negative right here, because we're tracking the y values of f. That's what f of x is. It's the y values of f, and they are negative right there. What does it want? It wants the product of those two things to be less than 0, similar to what we did earlier. So if we were to zone over here at negative 3, we know that that x value is negative 3. And then, of course, we have this asymptote at negative 2 as well to take into consideration. Everything left of this is, well, positive. Let's do that in purple. Everything left of negative 3 is positive, because as stated, the gradient of g is positive over there, and the y values for f are positive over there. Then in between negative 3 and negative 2, what we have is, well, the positive gradient from g and a negative y value over here from f, which means that product is negative in between these two values. And then to the right of this asymptote, we shall have that f is positive. It stays above the y value too. So all the y values for f over there are positive, and then the gradient for g just becomes more and more positive. So everything over there is positive as well. So what we are is stuck between these two values. Therefore, x is greater than and equal to negative 3 and less than 2. Why not less than and equal to? Well, this is still an asymptote and we still have to obey that law. So for our final question, they want the area of triangle ABC. So I'm going to need a couple of straight lines just to connect over here so we can see what we're doing. Right, so there we have an idea of what triangle ABC entails. So what we'll need, of course, is an idea of what to do. So to my money, the best strategy would be to create a y-intercept over here, and we'll call that point P. And for that y-intercept, what we'll need is a gradient and, of course, the equation following on that for line AC, which is going to give us what? Well, we already know that the coordinates over here at C is minus 3, or are minus 3 and 0. Just create some more calculation space over here. Well, now that we have that, we know that the formula for the area of a triangle is half base times perpendicular height. So we have the perpendicular height from there to there. So this triangle is covered in terms of perpendicular height. What we also need is the perpendicular height from there to there. And then for B, we have the coordinates 3 and 0. So if we were to be able to calculate the coordinates here at this newly created P, we will have the ability to calculate the base that we can use to calculate the areas in both triangles. So let's go for that. The gradient of AC then is equal to, well, what's our coordinates here at A is 29 minus 0, and then of course it's going to be 3 minus 3, which gives us a value of 29 over 6. From that we can use y is equal to mx plus c, and sub all of this in. That is going to give us, well, 0 is equal to 29 over 6, subbing in minus 3. Of course we are using point C over here with coordinates minus 3 and 0, plus C. From that, our C value, or our y-intercept, our y value, sorry, the y-intercept is going to equal 29 over 2. Therefore that equation, if we're interested, is equal to y is equal to 29 over 6 x plus 29 over 2. Now with that out of the way, we can calculate the length of BP, which is going to be 29 over 2 minus 3. But we can also do that directly within our triangle area calculation. So for triangle ABP, which is going to be this one over here that I'm marking, we shall have 1/2. It's the base. Well, it's just going to be 29 over 2 minus 3, and the perpendicular height, of course, which is just from 3 to 0. So it's that over there. So we'll have that times 3. And what we'll find is that is equal to 69 over 4 square units. So that's the area of triangle ABP. What about the area of triangle CBP? We'll do that a bit more formally. That's half base times perpendicular height, which is just 1 over 2, and then again that base calculation is 29 over 2 minus 3, which comes from this over there, and then, well, the perpendicular height is still 3, because in this case we're measuring from there to there. So 0 minus minus 3 gives us that length of 3, and that is equal to, well, once again, 69 over 4. And if we add them up, therefore the area of triangle ABC is equal to, well, 69 over 2 plus 69, not 69 over 2, 69 over 4 plus 69 over 4, and that's just equal to 69 over 2 units squared. Adieu. See, I invested 500,000 Rand for 5 years at an interest rate of 6.5% per annum, compounded monthly. Good on you, yeah? Calculate the effective interest rate of the investment, correct to 4 decimal places as required over there. So, what do we have? Well, that interest rate plus the effective interest rate is equal to, well, 1 plus the nominal interest rate divided by the period over which we're calculating to some interest period over there as well. So, therefore, our effective interest rate can be calculated as well. What are the inputs? 1 plus, well, what we'll have here is 6.5% over 12. That's the way the calculator can accept it nowadays. Multiplied by 12 minus 1. Let me just address that over here. You can, of course, ensure that it becomes 0.065 by dividing it by 100. If your calculator is not capable of doing this and accepting as is over there, most modern calculators, however, are capable of doing that. And your answer should be 0.0669718, which is then roughly equal to, correct to 4 decimal places, that's going to be 6,6972%, 4 decimal places as required. So let's just write that down there, 6,6972%. Hence, or otherwise calculate how much money you will get at the end of the 5 years. So for that, well, that's our standard growth formula. So to the power n input, well, principal is 500,000 Rand. Then we'll have, well, that's going to be 1 plus, it's going to be that 0.0669718 value if you have it stored in your calculator, or you can use that. And then, of course, that is multiplied by 5, because we already baked in, remember, all of this monthly compounding into this interest rate. That's why we use it as is, and that'll give you 691,409 Rand and 14 cents in the South African context. Rands and cents, as they say. A sports car is purchased for 800,000 Rand. After how many years will the value of the car be? 250,000 Rand. If the annual rate of depreciation is 20.75% per annum on a reducing balance method. Funnily enough, that is actually in line with reality. The moment any car leaves the lot, the purchasing lot, at the dealership lot, I should say, yeah, it's immediately worth quite a bit less. However, let's just have a look at what we're dealing with over here. We are dealing with depreciation and a reducing balance method, which means it's still compounding, but instead of plus, we're dealing with minus. So that's 1 minus that interest rate and that's all to the power n. Of course, let's just substitute what we have. Well, after that period, whatever it is, we will have a balance of 250,000 rand, or we will have a value of 250,000 rand, from where our principal was 800,000, or our brand new value. And then we'll have 1 minus, what is our interest rate? Well, they just gave us a per annum rate, which means we just divide that by 100 and we get 0.2075. And then n is what we are calculating for, of course. Well, if we divide both sides by 800,000, we'll get 5 over 16 as a nice and easy and simple fraction. Thus simplifies to this, and that's all to the power n, of course. And then we remember from logarithms that the answer to a log is an exponent. So the exponent being n over here, log, the base remains the base. So let's flip colors for that. So we'll have 317 over 400, and then of course that'll be 5 over 16 within our fraction, and that'll give us some rough answer. But remember, n in this case is equal to 5 years. How many years? A school is planning a mini school hall. School is planning to build a mini school hall. The cost is calculated to be 2 million rand in 10 years time. Okay, so that's pertinent information. That's pertinent information. On 1 January 2025, an initial deposit of 650,197 rand is made into the school hall project savings account. Okay, there we go. Interest is earned at 6.1% per annum compounded monthly for the first 5 years. On 1 January 2030, another amount of, well, some amount, X rand, is deposited into the savings account. The interest for the last 5 years is 7.47% per annum compounded quarterly. Determine the amount that was deposited into the savings account on 1 January 2030, i.e., that is, calculate the value of X. So, first things first, this thing assumes that this amount is successfully saved up eventually. So, let's start at the beginning. Well, for the beginning of the year, they deposited this amount of 650,197 rand. So, that's our initial principal amount that we're working with. And we're just going to do the normal growth compounding. So for our initial calculation, 650,197 rand acts as our principal amount, and we're just going to do the initial compound growth formula for this with this interest rate of 6.1% per annum compounded monthly. So that's going to look something like this. Well, that's our first. I'm going to have a subscript of 1 over there. And then our principal, of course, is 650,197 rand. That is, of course, what's this formula? 1 plus, well, 0.061 divided by 12, because it's compounded monthly, as they say. And 5 years, the first 5 years, so 5 times 12 is equal to 60, and that gives us an amount of, well, 881,000 rand, 881,392 rand and 29 cents. Then for the rest of this, we need to calculate what X is. Of course, that amount of x gets added onto this amount here. This 881,392 Rand and 29 cents has an X amount added on top of it, and then that amount grows for the rest of the period, which of course is 20 periods because we have a quarterly compounding that happens. So there's 10 years in total, so the last 5 years of this period gets multiplied by 4, so we have n is equal to 20 for this, and we have a new interest rate of 7.47% to work with. So remember, we have 2 million Rand that we get at the end of this period, so we know what our final amount is, and then our principal amount is, our new principal amount is 881,392 Rand and 29 cents, but we add some amount X to that to make up this entire new principal amount. That then gets multiplied by 1 plus 0.0747, which is our interest rate, which gets compounded on a quarterly basis for 20 quarters. So if we have a look at it, this still is the growth formula that we used to. Our compound interest formula. It's going to equal, let's see, 2 million on the left hand side, that is 891,392.29 plus x. So all multiplied by 1,0144785. Now, if we were to simplify all this, we'll just divide both sides by this value, 1.4478 and such. So that means 2 million divided by that gives us 1,381,392 Rand, 0.317. That's equal to 881,392.29 plus x. So let's clean this up slightly. Let's delete that. So if we finally subtract 881,392.29 from both sides, we'll have that x, this amount that was added at some point, is equal to 500,000 Rand and 3 cents is what you would get. But I'm going to assume for a deposit that 03 becomes irrelevant, which means we need to approach this logically. The amount that was added was 500,000 Rand. That's going to be some ugly editing. Well, for 7.1, this is something we should anticipate for every paper one. From first principles, let's see. Well, we have f of x over there, so let's just see what f of x plus h looks like. So we'll have x plus h all squared plus x plus h, of course. That is none other than x squared plus 2xh plus h squared plus x plus h. And then we are meant to subtract f of x. Well, that's the x squared, and over there we'll have x. So if we subtract that, this will be neat. What we'll have is 2xh plus h squared plus h, of course, and that is f of x plus h minus f of x, which is the bit that's on the numerator of our first principal formula. So let's get that sorted. F prime of x is equal to the limit as h strives to 0, of course, of f of x plus h minus f of x all divided by h. And wouldn't you know it, we have that quite available over there. Remember the limit notation, h strives to 0, so that'll be 2xh plus h squared plus h all divided by h. And of course our next step for f prime of x is going to be to, well, remember this entire process is about avoiding division by 0. So let's get a common factor on top in the numerator, and that'll be this. So f prime of x is equal, and since we are now substituting that 0 in over there, 2x plus 1. A final note, of course, is that, well, we can always just apply the power rule to our function so that we can turn this entire procedure into a proof, which means we'll just somewhere make a note that f prime of x is equal to, well, 2 times 1 gives us 2 over there, and then we subtract 1, so that's just going to be 2x, and the derivative of x is just going to be 1. So before you do this, determine f prime of x, if f of x is equal to 3x to the power 4 minus 1 half x to the power negative 2. Well, that's very direct. We can say that f prime of x is equal to, well, 4 times 3 is just 12, and it's x. 4 minus 1 is equal to 3. And of course for the next term, negative and a negative gives us a positive, and 2 times half is 1, which means this will be x to the power minus 3. Once we're done, then we have over here some Euler notation to deal with. Well, let's just simplify the expression inside the brackets first. First things first, we'll create two fractions with a common denominator of the square root of x, so that'll be that, plus 4 the square root of x, which means we'll have, well, square root of x is equal to x to the power a half, and that's 1, and 1 minus a half is just, well, a half. Over here what we'll have is 4x to the power negative a half, if we follow all our exponent rules over there. And the execution of this notation is that once the power rule is applied to the terms on the inside of the brackets, the notation can be left alone or, well, swept aside. I think that deserves a new color. So we'll have 1 half x to the power negative a half. Over here we'll have, well, okay, positive and a negative. Thank you, so negative. Half times 4 is just 2. And then that's x. Using a calculator to subtract 1 over here, we'll have minus 3 over 2. Remember, we're always just subtracting 1. Now, this is the next step is not necessary. Over here, we are done with respect to the way this question was presented to us. However, sometimes they will ask for the exponents to be left positive. So this will become 1 over 2. Well, then we can get back to square root of x. Then over here we'll have minus 2, of course, over, and then that x will be a square root and then cubed on the inside. Yeah, that's a decent exercise for anybody curious about, or anybody willing to practice their manipulations with respect to exponent laws, surds and such. Well, over here we're given a graph. It's defined by 2x cubed minus 3x squared plus cx plus 37. And And then we have some point B being an x-intercept of f with coordinates 1 and 0. Yes, yes, we will do this thing. Well, write down the length of OA. Well, this value D is of course the y-intercept, because this is written in the standard form for a cubic, which means that is 37, and 37 minus 0 is just 37 units. So write down, which means go read, go Google the diagram, and come back and report back. Now, show that the value of C is equal to negative 36. Well, what do we know about this graph? Well, we know that one of the x values that produces a y value of 0 is 1 here at B. So let's just sub that in. So 8.2 sub B 1 0 into f of x. Well, let's just see what that does. Remember, f of 1 is equal to 0 according to this. So we'll have 0 being equal to 2 times 1 all cubed minus 3 times 1 all squared plus c times 1 plus 37. Well, if we clean all this up, we get, well, that's just going to be 2. That's just going to be minus 3. Probably need a new color. All of that is minus 1. So we'll have minus 1 plus c plus 37. That's all equal to 0. If we clean this up, we get 36. And then we subtract 36 from both sides. Thusly, c is equal to negative 36. And would you look at that? That's exactly what they wanted. Now, determine the coordinates of P and Q, the turning points of F. So let's just write f of x now in its full form. We have 2x cubed minus 3x squared minus 36, because that is the value of c, x plus 37. So the coordinates of P and Q are the turning points of f. And at the turning points, if we were to draw tangents, those tangents would have gradients equal to 0. What does that mean? Well, we can get the general gradient for f of x. That's just called the first derivative. So 2 times 3, that gives us 6x squared minus 6x minus 36. So that's our general gradient. Now from that, we can now go and we can determine the specific x values where this happens to be true by putting those general gradients equal to 0, because we are working at the turning points. So let's get to that. So we'll have 6x squared minus 6x minus 36 all equal to 0. Let's trim this down because it's fat. I'm going to divide everything by 6. So we'll have x squared minus x minus 6, and that's equal to 0. This, of course, factorizes into x minus 3, x plus 2 is equal to 0. Nothing stops you from using the quadratic formula. Look over there. It's very relevant. Thusly, x is equal to 3 or x is equal to negative 2. So now to calculate the relevant y values, we'll know that for this one, we'll have f of 3, of course, and that's equal to negative 44. So that's that y value. And then over here, that y value will be f of negative 2, which will end up as 81. That is the purpose of this defining equation. So that's why I had the functional notation there, so that we can give back the actual answers to the question because they wanted coordinates. So P we can see is f of minus 2, and its x coordinate, its y coordinate is supposed to be positive and above over here, which means we'll have minus 2 and 81. And then Q we can see is to the right, so it'll have the positive x coordinate with the negative y coordinate. Right, so question asked and answered. Radio for 8.4. For which values of x is f prime of x greater than or equal to 0? So P we know is, well, minus 2 and 81. And this of course is 3 and negative 44. I rewrite those because we are interested of course in the x values. That's where minus 2 happens to be, and that's where 3 happens to be. Why is this important? Well, we can see over here what the gradient does just by looking at the graph, and then we can see the values where those behaviors shift and change. So for all values to the left of P, so to the left of P, our gradient, which is f prime of x, is greater than 0, or positive if you want to think about it like that. And then at P, of course, it's equal to 0. How do I know that? Well, obviously we can see we have an increasing function from left to right. So it goes up as I go from left to right. Then between P and Q, that gradient turns negative, or f prime of x is less than 0. Of course, after the turning point, turning, f prime of x is greater than 0 over there, or positive once more. And what are we looking for? Well, the areas where f prime of x is greater than or equal to 0, and that of course happens up till negative 2. So x is less than or equal to negative 2, because, well, we're allowed to be equal to 0. And then of course x can be greater than or equal to 3, because that's the other area where our gradient is positive. Well, for which values of k will g of x equal to f of x plus k have only one real root? So this g of x takes f of x and adds some constant value to it such that there is only one real root. So for this, our y values at the turning point become important, because what happens is, let's take scenario 1, is if we were to raise the graph completely, we know at some point Q will just touch this, we'll just touch the x-axis over there. So Q will go from there up to the x-axis as it's raised, and the moment it's greater than that, what happens is the graph lifts. I can do it that way. Well, the moment I raise the graph just a little bit more, what we'll find is there is only one real root, because the other turning point is now no longer below the x-axis. So when does that happen? That is when k is greater than this value of 44. So k should be greater than 44, the opposite of this negative. And then for p, the exact same logic can apply. We want a scenario where only this x-intercept remains, and of course our turning point P descends below the x-axis. So when does that happen? That is when K is less than negative 81. And that right there, I think, is that for that question. Right, determine whether f is concave up or concave down at the x-intercept. B is equal to 1. So for that, we have to remember that f prime of x was equal to what was f prime of x equal to? F prime of x was equal to 6x squared minus 6x minus 36. So what happens over there? Well, nothing really for this question. It's not that important, but we can calculate f double prime of x from it, which gives us an idea of the concavity depending on the x value. So that'll be 12x minus 6. So what are they asking? They are asking whether f is concave up or concave down at the x-intercept. So first things first, we can see that the graph is concave down in that general area that I'm currently messing around in, and then it's concave up. So where does this concavity change? Well, normally at our point of inflection, where our concavity is equal to 0. That is not what they are asking us today. Today they want to know what kind of concavity we have over there, which means we need f double prime of 1, and that is equal to 12 times 1 minus 6, because we substituted that value of 1 into f double prime of x, and that value is 6, which is greater than 0. So there it is concave up, because the value is positive or greater than 0. Oh, that kills this question. I think it's dead. It died an honorable death. An open box with a square base is made out of a given quantity of pre-cut cardboard sheet. The total surface area of the outside of the box is 300 centimeters squared. So over there we have surface, over there we have surface. What I want to get to is this top part, remember, is open. So we can sort of imagine that if it were to have a lid, that lid would fold away either this way or that way. Well, not that that's very terribly important right now, but it is something worth keeping in mind. Can I have my space back? Yes, I can. I'm allowed. Anyway, what does the question want? It wants us to determine the value of x for which the volume of the box will be a maximum. So let's have a look at how we tackle this. What we are going to need is the total surface area. So for that, let's just follow what's happening. It's a square base, which means we have x over there, x over there, and x over there. Because it's a box, we'll have h all over the place. Those are still x's, again, because of the nature of the box. So what does that mean? Well, we'll have a surface area front and back over there, which is h times x, front and back, and then left and right. So that will be multiplied by 4. So the sides of the box all have area x times h. So x times the height, but there are 4 of them. Then we need to add, well, there's a bottom to this container which has an area of x squared. Now the top, of course, is open, which means it's not there, so that is just going to be x squared. Now, what's the other piece of information we get given? We are told that the surface area of the outside of the box has some value. So 4xh plus x squared is of course equal to 300 centimeters squared. Now, they want the volume of this box to be a maximum. So we don't know what's happening here other than they need the volume to be maximized, and we can't deal with two variables. So given that this is surface area, we can go and write this entire equation that we've just created and make h the subject of the equation. So that will mean we'll have 4xh equal to 300 minus x squared. Let's change colors for a bit. Now we can just divide both sides by 4x, and that'll give us that h is equal to 300 minus x squared over 4x. So for now that is fine. We can now define the volume of this box in terms of x. But first, let's just see what we have. So the volume for the box is just going to be x times h, because it's a rectangular prism, and this open nature of the box doesn't matter anymore, because we are interested in the volume that can be contained inside the box with or without the top. So that'll just be x squared, and then h is defined of course by this expression, which is 300 minus x squared over 4x. I think we're allowed to change colors every now and then. From that, we shall have that the volume with respect to x is equal to 300 x squared over 4x. So that's that part. That's if we multiply over there, and then we subtract, well, x squared times x squared gives us x to the power 4 minus over 4x, of course, and then the whole thing is negative. Simplifying this gives us, well, the volume with respect to x is just 300 divided by 4 gives us 75x minus, well, x cubed over 4. So that part is not just highly relevant, it's what we need to maximize this entire thing. So let's just delete that and then take our volume equation over there. I think we can get rid of this as well. So what we have now, well, of course we want to maximize this thing, which means what we'll do is we'll find a derivative which will give us 75 minus, well, 3 over 4x squared. Then we can set that equal to 0, which means what we'll have is that 75 is equal to 3 over 4x squared, multiply both sides by 4 over 3, which is the reciprocal. There, that was the point. 35 via calculator. Therefore, x is equal to, well, plus or minus 10, which means x is equal to 10 centimeters, which renders this a cube, if you were to think about it. Probably. Or am I lying? No, it's not a cube. Now, hence we need to determine the maximum volume for this thing, and that is just going to be, well, the volume with respect to x, you should remember, is equal to 75x minus x cubed over x, and we'll just substitute the value 10 in there, so that's 75 times 10, sorry, that's a 4 over, well, 10 cubed over 4, which is equal to 500 cubic centimeters. Well, and that is that, apparently.